Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tare, and my last couple of videos were on some of the tools that we need to use to make logical arguments, in particular arguments in propositional logic. I've been talking about propositional logic, I think, for the last previous 6 videos. This is my 7th on propositional logic. When we're done with this, we'll get to something a little more complicated called predicate logic. That involves some things called predicates, but I'm not going to get into that today. Um, but anyway, let's just begin. So what can I say about making arguments in propositional logic? Well, the last couple of lessons I talked about some of the tools, and there are two types of tools for doing propositional logic. They're logical identities. That I talked about a couple lessons ago. Those are all of a form f is equivalent to g, where f and g are two Boolean expressions that are logically equivalent. So we can always substitute one for the other. Um, and the other tool we had was these things called rules of inference. Those were kind of simple logical arguments, or you can think of them as syllogisms, sort of like the Aristotelian syllogisms. And we can use those as tools as well. And just for completeness, I figured I'd show you guys those slides again. You can always go back to these if you want. Because I'm gonna give a couple examples of logical arguments, and these are the tools we're gonna use to prove the. We're gonna start with a set of premises, and we want to prove a conclusion. So we're gonna have to use some of these logical identities, and there's a total of 16 that I went over. And then there's also 12 rules of inference. I have to put these on 2 slides. So here's my first set of 6 rules of inference, and here's my second set. So if you like, you can always pause your video, or you can go back and look back at these. Maybe I'll try to go back and review them when I'm going through my logical arguments. I think I kind of rather not do that because it's pretty cumbersome. But anyway, at least you've got them on this video. You can stop your video. You can take a screenshot if you want, whatever you want. So you have all this information in front of you. If you're using my book, you can just flip through the book. Easier to do it that way, but anyway. So now here's the first argument. Here's the first thing we're gonna try to prove. So this is the first example. Um, so um, uh, I'll just read the example here. Where is it? Um, yeah. So there's 6 premises and a single conclusion. So the premises are as follows: if it rains on Saturday, I will not go to the baseball game. That's the first premise. The second premise: if I go to a baseball game on Saturday, I will buy a T-shirt. Third premise: if I get off from work early on Monday, I'll also buy a T-shirt. And the fourth premise: if I do not go to the baseball game on Saturday and I do not get off work early on Monday, I will not buy a T-shirt. And then the fifth premise is that it rains on Saturday. And the sixth premise is I do not get off from work early on Monday. And then what we want to conclude from this logical argument is that I'm not going to buy a T-shirt. And it turns out we can do a logical argument to make the conclusion. And I think if you kind of think about this scenario, it should make sense to you because there's sort of 2 possibilities of me buying a T-shirt. Either I buy it at the, I'm going to buy it at the baseball game if I go, and either, well, I guess I could buy it either if I go to the baseball game or if I get off work early on Monday. I can take the day off and buy a T-shirt on Monday. So there's 2 sort of scenarios where I can buy a T-shirt. And of course, if it rains on Saturday, I'm not going to go to the baseball game, so I wanted to buy a T-shirt there. But then if I don't get off work from early on Monday, then I won't buy a T-shirt in that case either. I think you can kind of see that if both of those things happen, both of those kind of contingencies, if it rains on Saturday and I don't get off work from early on Monday, I won't be able to buy a T-shirt. So that's what we want to prove. And And whenever you do a logical argument, you have to start by converting all your sentences to symbols, because this is math. We're doing math here, and math involves working with symbols, symbolic expressions, and each of these symbols represents a statement, a sentence. So this is just kind of an algebraic way of we're reducing English to logic, if you like, propositional logic, which is sort of like algebra, abstract algebra. So we have to first come up with a kind of a code for our sentences, and I'm trying to use a kind of a transparent code here. R, the letter capital R stands for it rains on Saturday. R for rain, if you like. B stands for go to the baseball game. T is the statement I buy a T-shirt. T for T-shirt. And E is that I get off work early on Monday. E for early. So I think those are kind of easy to work with. And anyway, so then now I've just said what the sentences are. I've given them symbols, and now I have to translate the argument. Remember, our argument started with six premises and a conclusion. So now the first premise was if it rains on Saturday, then I won't go to the baseball game. I think that's what I had. Yeah, yeah. So that's just R. If R, then not B. I think you can see that that's the kind of symbolic representation of that sense in propositional logic. And then the second premise, if I go to the baseball game, I'll buy a T-shirt. That's just B implies T. And then the third premise is if I get off work early on Monday, I'll buy a T-shirt. That's E implies T. Okay, and then the fourth premise is that if I don't go to the baseball game and I don't get off work early on Monday, that's not B and not E. That's the thing in parentheses on the left. If that's the case, then I won't buy a T-shirt. So that's not T. So those are the first four premises. The fifth premise is that it does rain on Saturday. That's R. Um, and the sixth premise is that I don't get off work early on Monday. So, and now we want to conclude that not T. Well, I mean, let's just think about the strategy here. How will we prove this? I mean, we know that if it rains on Saturday, then we won't go to the baseball game. So our fifth premise is R. It rains on Saturday. But then our first premise is that if it rains on Saturday, I won't go to the baseball game. Well, this has the form of modus ponens. If P then Q, P therefore Q. I mean, here P is R and Q is not B. So we can apply modus ponens to premise 1 and 5 and conclude not B. I think that's the first thing I do here. Yeah, first I wrote down the six premises. And when you make the logical argument, the first thing you always have to do is rewrite all the premises. I might as well show you this slide because this has all the premises written out again. But yeah, like I said, the seventh statement, this is something we're actually deducing. This is not a premise. But if you look at 1 and 5, so premise 1 is R, if R then not B, and premise 5 is R, and now we can apply modus ponens, which was our first rule of inference, and conclude not B. That's just the way we write that in parentheses next to it. The justification for this step is we're using assumption 1 and 5 and rule 1, which is modus ponens. So I'm just calling it R1 here. Okay, so that gives us not B. And now we want to conclude also not B and not E. Well, we were already given not E. That was premise 6. And now we're just using, what is it? There's another rule of inference, rule 11. I might as well go to that one. Yeah, it's kind of useful that I have all these here. Yeah, so the 11th rule of inference was composition. Remember, if we have two premises, P and Q, we can conclude P and Q. And so that's all we're doing here. So we're given not B is statement 7, and not E is statement 6. And we could just compose those two, not B and not E. And I'm doing them in the order in which it's given in the rule of inference. We're using not B first and then not E second. That's why I wrote 7 comma 6 and rule 11. Okay, well now, how do we conclude not T? Well, look at premise 4. Not B and not E implies not T, and we already have not B and not E. So now we can apply modus ponens again and conclude not T. So that's rule 1. Now this time we're using, we're starting with statement 4. That's the rule. I mean, it's just not being not E implies not T. And then rule 8, statement A is not being not E. Those are our first two statements, and the conclusion is not T. So that's the proof. And when we can translate that back in English, that means I'm not going to buy a t-shirt. So given all the information I've just spelled out in the first 6 premises, this is English now. This is a scenario in English. We make the conclusion that I won't buy a t-shirt. And all we did was we used pure logic to arrive at that conclusion. I think that's pretty powerful. Well, this was a pretty simple example. Now I'm going to give a more complicated example. So this one, yeah, we're gonna have to do a lot more work for this one. So here I'm just gonna read the statements again for the second example. First premise is if I eat out on Friday and Saturday night, I will gain 2 pounds. So I guess I like to eat out. I mean, I wrote this about, 5 or 6 years ago when I was eating a lot more. I don't eat it like a pig like I used to, but I guess there were times when I like to eat out, and I might have gained a pound just from eating out. Especially if you go to buffet, and there are a lot of buffets here in Las Vegas where I live. So this isn't totally, um, you know, unrealistic. So I guess you're supposed to imagine I'm going to gain a pound each night I eat out. So if I eat out both Friday and Saturday nights, I'm going to gain 2 pounds. And then the second premise is if I do not eat out on Friday night, I will not gain 2 pounds. Well, I guess that kind of makes sense because there's only 2 nights of the week I'm planning on eating out. Friday and Saturday nights, I'll have to eat out both of those nights to gain 2 pounds. If I just eat out on, if I don't eat out Friday night, that only gives me a chance to gain 1 pound by eating out on Saturday night. So that one kind of makes sense. And similarly, premise 3, if I do not eat out on Saturday night, I will not gain 2 pounds. Same idea. And then number 4, I will go on a diet if and only if I gain 2 pounds. So if I gain 2 pounds, I'm too heavy and I have to go on a diet. That kind of makes sense. Number 5, I will eat out on Friday night if and only if I have a date for that night. Well, yeah. So, um, if I get lucky and I have a date for Friday night, I want to take my date to a nice, fancy buffet. We'll both pig out and we'll have a good meal. And, I'll probably gain a pound from that, but, as long as I'm having a good time, my date is 2, it doesn't really matter. And then 6, similarly, if I eat out on Saturday night, I will eat out on Saturday night if only I have a date for that night as well. Well, I don't know if it's gonna be with the same woman or not, but whatever. I mean, maybe I'll have 2 dates. Maybe I'll get really lucky, either with the same woman or with 2 different women, and I'll eat out both nights, but that'll make me gain 2 pounds. Okay, and now, say I have a date for Friday night. That's our 7th premise. But I don't have a date for Saturday night, so I got lucky with one of the women. But, so that means, and then our conclusion is that I do not go on a diet. Well, I think it's kind of, if you think about what's going on, I think this should make sense because, I'm only going to gain 1 pound from going out one night, and I said I was only going to go on a diet if I gain 2 pounds, right? So I didn't gain enough weight to go on a diet. So that's kind of how this argument's going to work. But we have to translate this into math. And it turns out this one's going to be pretty complicated to actually prove. But we have to do the same thing we did last time. We have to encode each of our sentences. And since some of these sentences are kind of similar, I'm giving them subscripts here. So I'm not just using simple letters anymore. But you can just think of these as more complicated letters. So I have E1, which says I eat out on Friday night. That's my first scenario for eating out. And then E2 is I eat out on Saturday night. And then G is I gain 2 pounds, G for gaining. D is I go on a diet, D for diet. D1, I'm using date and diet. Unfortunately, those begin with the same letter. That's why I say date for Friday night, D1, and date for Saturday night, D2. Um, Anyway, those are the statements encoded as symbols. And now I think I'll just cut to the chase and show you the. Oh no, actually, I'm not going to do that yet. So now we have to encode our premises and our conclusion. And this is just how we do it. And I'll just read out what they say. So E1, remember, was eating out on Friday night, and E2 was eating out on Saturday night. So the first sentence is just a mathematical way of saying that if I eat out on both Friday and Saturday nights, then I'll have to go on a diet. G for go on a diet. And then our second premise was that if I don't eat out on Friday night, I won't go on a diet. That's not E1, applies not G. And similarly, the third premise was if I don't eat out on Saturday night, I won't go on a diet. So that's not E2, implies not G. Okay, and then premise 4 was G is equivalent to D. Remember what I said earlier? I said that I'll go on a diet if and only if I gain 2 pounds. So that means that if I do gain 2 pounds, I have to go on a diet, but if I don't, then I'm not. That's what equivalence means. Um, anyway, and then yeah, 5 and 6 are also equivalent. So I said if I have a date on Friday night, I'm gonna eat out on Friday. That's all that's saying. I'm gonna eat out on Friday night if and only if I have a date. I'm not gonna eat out by myself. I'm only gonna eat out if I have a date to go with. And similarly, premise 6 was that I'm gonna eat out on Saturday night if only if I have a date for Saturday. So yeah, and then our seventh premise was I have a date for Friday night. That's D1. And our eighth premise is that I don't have a date for, or no, the D1 was I have a date for Friday night. And then I said I don't have a date for Saturday night. That's not D2. And that means the conclusion, the thing we want to have to prove here is that I don't have to go on a diet. So even though it seems kind of intuitively obvious, you actually have to do a fair amount of work to prove this one. And you can see what I've done here. So the first 8 of these statements are our first 8 premises. I just rewrote them here. And now we have to prove a bunch of other statements before we can actually prove the conclusion. In the last example, I think I only had to prove, 2 things after the premises. Now here I'm proving, it looks like 9 things. Statements 9 through 16, and the conclusion, which is sort of like statement 17. So let's just go through this. So the ninth statement, and it looks like we're using, what am I using here? Um, L15. This is logical identity 15. I might as well go to that one because I don't remember offhand which one that was. You have to go all the way back here. Yeah, L15 was the definition of equivalence. To remember, there's 2 definitions of equivalence. One, P is equivalent to Q, is the same thing as P implies Q, and Q implies P. So that's what I'm using here. Might as well go the short way. So yeah, so let's just see that. So remember, we're using 6, which is an equivalence. D2 is equivalent to E2. So that's just that I'm just rewriting this using this definition of yeah. I guess I just use 6. Yeah, for the logical identities, you only have to use 1 premise. So in this case, I'm using 6. I'm just rewriting what it means for D2 and E2 to be equivalent. That's just saying D2 implies E2 and E2 implies D2. Okay, so that's pretty clear. And then for number 10, I'm using another logical identity, L7. Yeah, I'm using the last statement I just wrote down and the logical, the rule of inference 7. I might as well look that one up too. Yeah, I think I better go the short way. Yeah, so here, L7 is commutativity of conjunction. Yeah. Oh, yeah, that's all I'm doing here. So, yeah, so notice for 10, all I'm doing here is I'm switching around the sides of 9. That's a commutativity of conjunction. Notice that the operator in the middle of the ninth sentence here is and. That's conjunction. So remember, conjunction is commutative. P and Q is equivalent to Q and P. So here P is D2 implies E2. Q is E2 implies D2. I'm just flipping them around. That's all I'm doing there. And then for 11, I'm using a rule of inference here. I'm using 10, which is a conjunction. And oh yeah, this one I'm not even going to look up. So we have a conjunction here, right? And remember the rule of inference for, I think this is called simplification of conjunction. I don't remember the name of the rule of inference. I think it's called simplification. But if you have a conjunction of two things, P and Q, you can always include P. I might as well look this one up. Yeah, I'm doing the wrong ways. This, okay, so yeah, so that's L10. Which one am I? No, I'm using a rule of inference. R10. Yeah, simplification. P and Q implies P. Right. Let's go the long way back. Yeah. So anyway, kind of pain to keep going back and forth with these slides here, but that's all I'm doing here. I used the 10th rule of inference, which only has one premise and one conclusion. And then for statement 12, I conclude not F2. How did I conclude that? I used, or not E2, rather. I'm using another rule of inference here. Oh, yeah, this one's modus tollens. I remember. R2 is modus tollens. So let's see what 11 and 8 is. 11 is the last one we just proved. E2 implies D2. And then 8 was not D2. Right. Remember, P implies Q, not Q, therefore not P. That's modus tollens, which is the converse of modus ponens. That's what we're using for 12. So we start with E2 implies D2, and then we have not D2, that's 8, and we conclude not E2. Right. And then for 13, we're using modus ponens this time with statements 3 and 12. So let's look at 3 again. 3 is not E2 implies not G. 12 is not E2, therefore not G. Remember P that, so modus ponens starts with if P then Q, P therefore Q. Well, in this case, P is not E2, and Q is um, that, or no, P is, yeah, yeah, P is not E2 and Q is not G. So using modus ponens, we conclude not G, which is Q in that case. Right, and then 14. Here we're using another logical identity. We're using L7, which we already used. Wait, I'm doing the wrong one. L15. L15, we already used that one. That was the definition of the second definition of logical equivalence. So we're using that with proposition 4, premise 4, which is G is equivalent to D. So we can rewrite G is equivalent to D as G implies D, or D implies G. That's what 14 says. And then again, we can use commutativity, so we can rewrite that as D implies G, and G implies D. And now, finally, well, not quite finally, but for statement 16, we conclude D implies G. How do we include that? We used rule 10, rule of inference 10, which we already used before. That was simplification. Remember, we have a conjunction, D implies G and G implies D. We can automatically conclude the first thing here. That's why we had to commute it first, because the way the rule is stated, we have to use the verbs. We remember we start P and Q implies P. That's how we stated Rule 10. That's the only reason we had to switch these things around. Um, so finally, for 16, we have D implies G. Now we're almost done. And finally, we're using Rule 2 at the end, which is modus tollens again, the converse of modus ponens. So we start with 16, that was the last thing. D implies G. We also use 13, which is not G. Remember, if we have D implies G and not G, we conclude not D. So now we're done. That's what we wanted to prove. That I don't have to go on a diet. So we had to do all that work just to prove that I don't have to go on a diet if I eat out just one night this weekend. If I ate out 2 nights, I would, but just one night, I don't have to. So even though it's kind of intuitively obvious, sometimes you do have to do a lot of work to actually prove it rigorously. I think this is one reason why sometimes computers have a hard time, solving problems that are intuitively obvious to humans. That's one thing computers don't have. Computers don't have intuition. We can program a computer to apply logic the way I'm showing you here. That's what's kind of beautiful about it. We could use AI. AI can do logic if it's sophisticated enough. But one thing AI can't really do is it doesn't have intuition. It doesn't. Things aren't obvious to computers. They have to prove everything. They're like completely logical. So, that can be a drawback sometimes. But anyway, this could at least in principle be done on a computer. So anyway, that concludes my lesson for today on arguments and propositional logic. So thank you for watching. Long live math, and I'll see you guys next time.